Hi, Advanced Algebra 2. Let's talk about some properties now of rational exponents and radicals. Alright, so the properties of integer exponents that you previously learned, we reviewed them from Algebra 1, can also be applied to rational exponents. And remember, a rational exponent is an exponent that you can think of in ratio or fraction form. So if you look at the different properties here, we'll just go through them briefly, okay? And the examples will probably help you the best, the column over on the right. So the product of powers, if you're multiplying the same bases, then you know you can just add the exponents. And so it works with rational exponents as well. The next property, a power of a power. So when you are raising a power to a power, whether the powers are integers or fractions, you can multiply those powers. And these two properties are just related. Negative exponents, you know that if something's raised to a negative exponent, you can rewrite it as a positive exponent by dropping it into the denominator if it starts in the numerator, or putting it up in the numerator if it started in the denominator. So for a zero exponent, it still equals 1, although you cannot raise 0 to the 0 power. If you're dividing, so quotient of powers, if you're dividing same bases, you can subtract those exponents, so even if they are fractions. And then finally, if you're, again, this is like the power rule, but if you have things that you're dividing, like 27 divided by 64, and you're raising it to a rational exponent, it's the same thing as taking the top number to that power, raising them both, divided by the bottom number to that power. And sometimes that will help you simplify. So we use these properties to manipulate the problems that we're given to try to simplify. So your notes just tells you to refresh your memory of these properties. We will not be doing, though, expiration 1, that list after refreshing your memory. So we'll just work some examples. So simplify rational exponent. That means we're going to do what we can with the properties, but we're not going to get on our calculator and estimate what the values are. Just simplify. So notice we have 7 to the 1/4 power times 7 to the 1/2 power. So if your bases are the same, you can just add those exponents. So 1/4 plus 1/2. Now you can use your calculator to help you, or you can just get common denominators. So if we change 1/2 to fourths, that's the same thing as 2/4. So now we have 1/4 and 2/4, so that would be 7 to the 3/4 power. And that won't simplify any further for us. Now here we have 6 to the 1/2 times 4 to the 1/3. We cannot simplify inside because these are not same bases, so we can't add those exponents. But we can raise each of them to the second power. So we're going to take 6 to the 1/2 power, and we're going to multiply those powers together. And then we're going to have 4 to the 1/3 and raise that to the second power. So we'll get 1/2 times 2 is simply 1. So this will give us 6 to the first power times 4 to the 2/3 power. And this is awkward, but that's as simple as we can get that without estimating. Excuse me. All right, C is a lot the same way. We cannot simplify what's inside, but we can do a couple things. First of all, I'm going to rewrite this in positive exponent form. So I'm going to say 1 over, and then write this as 4 to the 5th power. Oh, they are both 5th powers, however. So if our powers are the same, then we can multiply those bases. So that's the same as 12 to the 5th power. And then it's going to be raised to the positive 1/5 power, now that I put it in the denominator. I'm not sure what this line is right there. It's not a part of the problem. So now we'll have 1 over. When we raise a power to a power, we multiply. So 5 times a 5th is simply 1. So that will end up being 1/12. Circle this one. Now, finally, we have 5. This is to the first power divided by 5 to the 1/3 power. See how our bases are the same, 5, and we're dividing. So we can take the biggest exponent and subtract the smaller. and it's going to end up on the numerator. So 1 is the same as 3/3. So 3/3 minus 1/3 will leave us with 2/3. So we'll have 5 to the 2/3 power. All right, now look at that core concept. So now we have properties of radicals, and we're going to use these properties to work some problems. We're actually not going to do this exploration 3. So the product property, notice, and the examples will help you the most. If you're multiplying two roots together that are the same, you can put their bases. So the cube root of 4 times the cube root of 2 is the same thing as the cube root of 4 times 2, or 8. And then that allows you to simplify it. Now the quotient property, quotient, means divide. So the 4th root of a number divided by the 4th root of another number, you can rewrite it as those two numbers divided and then taking the 4th root. So 162 divided by 2 is 81, and you can take the 4th root of 81. So we just use these properties if they're going to help us simplify the expression into an easier form. Now on your note sheet, go to where it says example 2. It says write a few problems from exploration 3 as examples of how to use the properties of radicals. So I've got some problems for you here, and just write these down in the space. Start with A in the upper left. So we're going to take the square root of 3 times the square root of 12. It's a property that if the roots are the same, they're both square roots, you can combine the numbers underneath. So we can rewrite that as the square root of 3 times 12, or 36. And then the positive square root of 36 is 6. All right, now write down B. We've got the 3rd root of 5 times the 3rd root of 25. Since our roots are the same, we can multiply those numbers underneath. So 5 times 25 is 125. And then the 3rd root of 125 is 5. Now hopefully that you recognize that, but if not, you can put it on your calculator or look on your roots and powers chart. All right, C, let's try another one. So we have the 4th root of 27 times the 4th root of 3, and we're asked to simplify. So they're both 4th roots, so we can rewrite them as the 4th root of 27 times 3, which is 81. And then we've done this a few times. The 4th root of 81 is 3. All right, now write down D. We've got the square root of 98 divided by the square root of 2. Notice they're both square roots, so we can go ahead and combine this problem all under one square root. And sometimes that will help us to simplify it, because 98 divided by 2 is 49. The square root of 49 is 7. It works with other roots as well. So if you write down the problem for E, the 4th root of 4 divided by the 4th root of 1024. So we can rewrite that as the 4th root of 4 over 1024. And then if we reduce that fraction, that becomes 1 over 256. Now we can just continue using those properties, and we can split that up. And so we've got the 4th root of 1 over the 4th root of 256, because when we do that, we are able to simplify it. So 1 over 4. So we can use those properties kind of both ways, if you want to think of it like that. Now, finally, let's look at F. So we have the 3rd root of 625 divided by the 3rd root of 5. So neither one of those are even 3rd roots, but you can go ahead and divide them and put them all under 1/3 root. And when you do that, you end up with a number that does have an even 3rd root, which is 5. So again, we use the properties when we are asked to simplify problems. Simplify means that you just put them in the simplest form without grabbing a calculator and estimating. All right, continue on your note sheet. An expression involving a radical with an index, that's the root, in simplest form, or is in simplest form when these conditions are met. So no radicands have perfect powers as factors other than ones. No radicands contain fractions, and no radicals appear in the denominator of a fraction. So radicand is what is underneath the sign. So to meet the last two conditions, we might have to rationalize a denominator. So that involves multiplying both the numerator and denominator by an appropriate form that is equivalent to 1. All right, so let's write these expressions in simplest form. So we have the third root of 135. So 135 is not an even third root, but let's, like we do with square roots, let's break it down. So we know that it can divide by 5, and 135 divided by 5 is 27. So this is the same thing as the third root of 27 times the third root of 5. So we're just using this property backwards, the multiplication or product property. So now we can evenly take the third root of 27, which is 3. And when we do that, it comes out of the radical sign. But we're left with the third root of 5. So that is that expression in simplest form. Now the square root of 72, so we'll break it into square root of 9 times the square root of 8. I'm going to try a different pair because I bet there's a pair that has a bigger perfect square. How about 36 and 2? Square root of 36 is 6, but we can't evenly take the square root of 2, so that stays under the radical. All right, third root of 108 times the third root of 4. So there are a couple different ways that we could go about this problem. So I'm going to look at the cube root of 108, and I'm going to, let's see, divide it by 4. 4 times 27. So I'm going to rewrite the cube root of 108 as the cube root of 27 times the cube root of 4 times another cube root of 4. So I can take the cube root of 27, that is 3, and then I'm left with the cube root of 4 times the cube root of 4. So I can multiply those back together and get the cube root of 8. Now I'm going to see if I have any perfect cube roots in 16. So I think of factors of 16. And I know that if I divide it by 2, I will get 8. So I can take the cube root of 8, which is 2, multiply it by 3, which is 6, times the cube root of 2. Now again, sometimes you have to use multiple properties and do a lot with the problem to get it down to simplest form. And the way I simplify it may not be the same path that you take to simplify. But notice that we've got no radicands or numbers underneath that have perfect powers. So this number 5 is not a perfect third root, or it doesn't have any factors that are. 2 is not a perfect square root, doesn't have any factors that are. And 2 is not a perfect cube root. That none of the numbers underneath contain fractions, and that we have no radicals, so that's the root sign in denominators. All right. Now, no radicals can be left in denominators, and so sometimes we need to rationalize the denominator. So we've rationalized square roots, but now let's rationalize other roots. What we're going to do, method 1, is we are going to multiply the denominator by an expression with the same nth root, and then an expression under root that has the same base, but so the power will add up to the root power when multiplied. Now, I'll show you what I mean. So, third root of 1/6. Let's split that up into the third root of 1 divided by the third root of 6. So the third root of 1 is 1, but we cannot leave this in the denominator. So now what we're going to do is I'm going to read that statement above again, and I'm going to actually do it as I read it. So I'm going to multiply the denominator by an expression with the same nth root. So that's going to be third root. And an expression that has the same base, so that's 6, but a power that will add up to the root. So this is to the first power, so I want this to be the second power. And then we're going to multiply same up here, so that this is the equivalent of 1. Now watch what's going to happen here. So we get the cube root, and I'm just going to go ahead and square that 6 up top, just to clean that up a little bit. And then here, when I multiply these together, I get the cube root of 6 to the first times 6 to the second, which ends up being 6 to the third power. And then 6 to the third power, and we take the third root of that, that simply equals 6. Now I check and I see if any of my factors of 36 are third roots. So I've got 1 and 36, I have 2 and 18, nope. I have 3 and 12, 4 and 9, nope. So I can leave that as the third root of 36, all divided by 6. Now look at the next one. We've got the fifth root of 7 over the fifth root of 8. So we're going to multiply by same root and then same base to the fourth power, because this one's to the first power, so I want to multiply it by a power that when we add them, it will equal the root, so it will equal. All right, so now this is going to be the fifth root of 7 times 8 to the fourth. Now if you do that, you will get 28,672. And then here we will end up just getting the fifth root of 8 to the fifth. All right, so the fifth root of 8 to the fifth is simply 8. Now I wonder if there's any fifth roots in here. I know that a common fifth root is 32, so I'm going to take that and divide it by 32. Yes, and I get 896. All right, so I can take the fifth root of 32, which is 2, and I'm left with the fifth root of 896. Now I'm going to see if 32 divides into that. It does. 28. So another fifth root of 32 is 2, multiplied by 1 out front is 4, and then fifth root of 28. All divided by 8. Almost done. I can divide out 4 here. So I'll get the fifth root of 28 all over 2. So all I'm doing is just taking what I can to simplify and taking out any of the roots. In this case, it'd be fifth roots. Okay, last couple problems. So multiplying, rationalizing when you've got situation like in these method 2 examples. So notice it's an expression with a root. So we're going to multiply by the conjugate. So the conjugate is the same terms but opposite signs. So instead of 5 plus the square root of 3, I'm going to multiply this by 5 minus the square root of 3. Top and bottom, because this is the equivalent of 1. So up top, I'll simply have 5 minus the square root of 3. Here, I'm going to have the first term squared, which is 25, minus the second term squared, which is 3. Because you know, a plus b times a minus b is the same thing as a squared minus b squared. So 5 minus the square root of 3, all divided by 22. Here, we'll take 6 plus the square root of 2, multiply top and bottom. So we'll have 3 times 6 plus the square root of 2. And then the bottom we'll get 36 minus square root of 2 squared is 2. So we can or we don't have to multiply that 3. I'm just going to leave it factored out. And then 36 minus 2 is 34. And so that's our final expression. So this is actually equivalent. It's saying the same thing as this, but it's just doing it without a radical in the denominator. All right, that concludes our notes as using properties of rational exponents and radicals in section 5.2. And these are the part 1 notes.